Hello students, in this video we will discuss some methods to find particular integral of given homogeneous linear partial differential equation. Here first we discuss some short methods, some specific methods to find particular integral, and in further next video we will discuss general method to find particular integral. So first we discuss when we have f d prime z is equals to function of xy. This is a given homogeneous linear partial differential equation with constant coefficient, and the right hand part, which is function of xy, is in a particular form function of ax plus by. This phi is any function in terms of ax plus by. It means x and y should be in a relation of this type. Ax plus by, a and b are some real constant. So if right hand part is in this form, we can write particular integral just 1 upon f d prime phi of v, where v is ax plus by, taking ax plus by is equals to b, and its particular integral will be 1 upon function of a and b. Just replace d with a and replace d prime with b and integrate phi of v n times with respect to v, n times the order of given homogeneous differential equation. So whichever is order, integrate phi v that number of times. If given equation is of second order, we have to integrate it 2 times. If given equation is of third order, we have to integrate it 3 times. So n times we have to integrate when the order of homogeneous equation is n. Here a condition is that f of AB must be non-zero. In that case we can apply this approach. But if f of AB is 0, in that case what we do, if f of AB is 0, it means BD minus AD prime is a factor of given equation FD D prime, or if it is a repeated factor of nth order, if it is n times repeated factor, then the pi about this factor can be written as x raised to power n upon b raised to power n factorial n into phi of ax plus by only. Just the power of x is n, how many times bd minus ad prime repeated, upon b raised to power n upon factorial n. Here n, how many times bd minus ad prime repeated. So if f of ab is 0, then we apply this approach. Now we explain this both case using some example. So first we take a problem, d square plus 3d d prime plus 2d prime square z is equals to x plus y. First we write its CF. Its auxiliary equation is m square, replace d with m square plus 3m plus 2 equals to 0. So m plus 2, m plus 1 is a factor of given equation of this auxiliary equation. So m is equals to minus 1 and minus 2 are roots. So about minus 1 and minus 2, CF is phi 1 y minus x plus phi 2 y minus 2x. Now we have to find particular integral. To find pi is equals to 1 upon f dd prime, and f dd prime is d square plus 3dd prime plus 2d prime square of x plus y. Here taking x plus y as v, order of homogeneous equation is 2, so we will integrate v twice with respect to v, and 1 upon f of ab, a is 1, coefficient of x is a, coefficient of y is b. So replace d with a, that is 1, replace d prime with b, that is 1. So it becomes 1 square plus 3 plus 2, that is 6. Sorry, it becomes 6, 1 by 6. Now we integrate it twice. So first time we get v square by 2, and second time it gives v cube by 6. So it becomes Pi becomes 1 upon 36 V cube, where V is x plus y. So Pi become 1 upon 36 x plus y whole cube. And complete solution z is equals to Cf plus Pi, that is z is equals to phi 1 y minus x plus phi 2 y minus 2x plus 1 by 36 x plus y whole cube. Now let's take another problem. Del 2z upon del x square plus twice del 2z upon del x del y plus del 2z upon del y square equals to 2x plus 3y. We can rewrite it as in this way. First, write auxiliary equation, replace d with m and d prime with 1. We get m square plus 2m plus 1 equals to 0, that is m plus 1 whole square equals to 0. It means m is equals to minus 1 and minus 1. Minus 1 is a repeated factor, 2 times repeated. So Cf should be phi 1 y minus x plus x time phi 2 y minus x. So this is complementary function of given equation. Now we have to find particular integral. To find particular integral, which is equals to 1 upon f dd prime. Here f dd prime is d square plus 2 dd prime plus d prime square, or d plus d prime whole square of 2x plus 3y. Here, if when we compare it with ax plus by, a is equals to 2, b is equals to 3, and 2x plus 3y is v. And now replace d with a, that is 2, and replace d prime with b, that is 3. It becomes 1 upon 2 plus 3 whole square, that is 1 upon 25. And integrate v twice with respect to v, it becomes v square by 2 and further v cube by 6. So it becomes 1 upon 150 v cube. So this is Pi, 1 upon 150 into 2x plus 3y whole cube. This is Pi of 2x plus 3y about this FDD prime. Hence complete solution z is equals to Cf plus Pi. There is one more problem. D square minus 2d d prime plus d prime square z is equals to 10y plus x. First calculate Cf. So its auxiliary equation is m square minus 2m plus 1 equals to 0, or m minus 1 whole square equals to 0. It gives m is equals to 1 and 1. So Cf is phi 1 y plus x plus x times phi 2 y plus x. Now we will write it Pi 1 upon f dd prime 10 y plus x, or 10x plus y. A is 1, b is 1, and x plus y is v. So it becomes 1 upon d minus d prime whole square 10 y plus x. When we replace d with a, which is 1, and when we replace d prime with b, which is also 1, it becomes fab equals to 0. And when fab equals to 0, this here we use second approach. So x raised to power 2, how many times d minus d prime this factor appear? It is a repeated factor, 2 times repeated factor. So x raised to power 2 upon b raised to power 2, b is 1, coefficient of y, into factorial 2. So x square upon 2 10 y plus x is a particular integral of given problem. So x square by 2 10 y plus x is a Pi. Hence complete solution is z is equals to Cf plus Pi. Here we have another problem. D cube minus 4d square d prime plus 5d d prime square minus 2d prime cube. Z is equals to exponential y plus 2x plus y plus x raised to power half. So first we calculate its Cf. For that we write auxiliary equation, find its roots. Its roots are 1, 1 and 2. So about repeated factor 1, Cf is phi y plus x and x phi 3y plus x, and about 2 it's phi 1 y plus 2x. Now we calculate pi. Here we have to calculate pi two times. First we have to calculate pi for exponential y plus 2x, and second time we have to calculate pi for y plus x raised to power half. So one by one we will calculate pi for both. So first we will calculate pi for exponential y plus 2x. So pi about this is equals to 1 upon f dd prime. Here f dd prime is d minus d prime square d minus 2d prime of exponential y plus 2x. Here a is equals to 2 and b is equals to 1. When we compare is phi of ax plus by, a is 2, b is 1. It becomes exponential v. Here the denominator of ab becomes 0 due to the factor d minus 2d prime. When we replace d with a, that is 2, and d prime with 1, second factor d minus 2d prime becomes 0. But the first factor d minus d prime whole square, this is non-zero. So we calculate pi 1 upon d minus d prime whole square exponential v as first approach, and about the factor d minus 2d prime we apply second approach. So first we calculate pi for 1 upon d minus d prime square exponential v. It gives us, replace d with 2 and d prime with 1, it gives us 1 upon 1, and integrate exponential v 2 times. The order of this factor is 2, so we will integrate it 2 times. It gives us exponential v exponential 2x plus y. Now we will find pi of exponential 2x plus y about d minus 2d prime. When we replace d with 2 and d prime with 1, denominator become 0. So here we apply second approach, and according to second approach, how many times it appears d minus 2d prime? It appears 1 times only. So x raised to power 1 upon factorial 1 into b raised to power 1, and b is 1 raised to power 1. So it gives us 1 into phi of ax plus by, and phi of ax plus by is exponential 2x plus y. So x into exponential 2x plus y is pi for exponential y plus 2x about this term. Now we calculate pi for x plus y raised to power half. So here when we replace in d with 1 and d prime with 1, here in this factor becomes 0, but this factor is non-zero. First we calculate pi of x plus y raised to power half about this second factor. So first we can find the pi of x plus y raised to power half about d minus 2d prime, and whatever result we get here, then we find pi of this resultant function about 1 upon d minus d prime whole square. So here we replace d with 1 and d prime with 1. It gives us 1 upon minus 1. 1 minus 2 gives us minus 1, and integration of v raised to power half, this is of order 1, so we integrate it 1 time. It gives us v raised to power 3 by 2 upon 3 by 2. So when we simplify it, we get minus 2 by 3 v raised to power 3 by 2. Now d minus d prime whole square becomes 0 when we replace d with a1 and d prime with 1. So here we apply second approach, which gives us x raised to power 2, as this factor is appear 2 times. X raised to power 2 upon 1 raised to power 2, that is b raised to power 2 into factorial 2 of phi v of phi of ax plus by, that is v raised to power 3 by 2. When we simplify it, we get x minus x square by 3 v raised to power 3 by 2, or minus x square by 3 x plus y raised to power 3 by 2. So this is pi about x plus y raised to power half, and this is x exponential 2x plus y is pi about exponential 2x plus y. Hence total pi is x exponential 2x plus y minus x square by 3x plus y raised to power 3 by 2, and complete solution is z is equals to cf plus pi. This is general solution of given problem. So hence that's all about this method, and there are some problem based on this method.